Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and privilege to be serving you here today, as it is every day. Step inside my virtual classroom, and I'm going to introduce you to proofs. Now, a proof is a list of circumstantial evidence that leads you to a conclusion that you've proved. A proof is something that you prove. And in math, proofs are used to validate properties and theorems and definitions and things like that. Specifically, the word theorems here, because everything else is kind of a basis of something else. A formula is a basis of mathematical properties and things like that. But a proof is something, a theorem is something that we can use to help us expedite things in math down the line, such as, which I'll prove today with you, vertical angles are congruent and alternate interior angles are congruent. So I'll make sure to do those two proofs with you as well. Now, proofs are used in a lot of different things other than just math, guys. You can prove anything under the sun for any reason. I proved that you were watching TV last night because the TV was on and I saw you. I don't know. There are a lot of different ways you can prove different things. In fact, I started to write one out here, and I didn't know what I wanted to do with it, but you can prove someone to be guilty of murder for a certain reason if you have enough circumstantial evidence backing it up. A motive, saying like, oh, you knew they hated her, they knew he wanted to kill her. And then you see the weapon with the blood and the DNA and time and location. They're at the place and there are witnesses and stuff. Eventually enough things stack up to say there's 100% indisputable evidence, which hopefully we weren't framed or anything like that, but 100% indisputable evidence which ends up saying that a murder occurred. So that's an example of proving something. I mean, what's the word? A prosecutor has to go really far and beyond to convince 12 jury members and make sure that kind of happens. So that's an example of a proof. Here's another proof that I'm not going to get too deep into, but it's the Pythagorean theorem proof, which I already kind of drew it out here. The way to do the Pythagorean theorem proof is you draw one square, this square on the outside. Hopefully you can kind of see that that's a square. You draw one square and you inscribe another square inside of it right here. And we know what squares have: right angles and equal sides. So within any of these squares within here, guys, we can make a right triangle. Now, right triangle, we can give some of these lengths here because it's a square of equal sides. That means you can make A right here, right here, right here, and right here. Those will all be the same value, whatever they are. And these can all be B's, B, 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 and B. And because this is a square on the inside, all these will be equal length. That's all C. So what you do in this proof is you make a statement that says the area of this entire thing, which every side is A plus B. So when you square it, that's how you get the area. So the area of this entire thing is equal to the sum of the areas of each individual part here. The sum of this square plus the sum of these the area of this square plus the area of 1, 2, 3, 4 triangles right here. And what happens when you expand this out, and you expand this out the right way, you subtract the 2ab from both sides, you get a squared plus b squared equals c squared. That is indisputable proof that every right triangle, the sum of the squares of the legs equals the square of the hypotenuse. That is indisputable. I didn't even use an example. And here's the thing. You can't prove by example either. I can't state, even if I see a million fire trucks, they're all red, that is still proving by example. I can make a conjecture. It might even be true. But once you see another fire truck that's green, the proof is gone. I didn't do enough to kind of state that proof. I'd have to go all the way to the headquarters of fire truck manufacturing and painting making and things like that to go prove that the only paint they have in their place is red. You know what I mean? Or something like that they only order red paint, that there are no other chemicals that can change the colors and things like that. So, proofs have to go a little deeper into that. And what we're going to be doing right now is we're going to look at what are called two-column proofs. A two-column proof is where you lay claim to a statement and a reason. So for every statement, there has to be a reason behind it. Otherwise, the statement is dry. You can't make the statement as a result of that. So we're going to do a two-column proof together in proving that vertical angles are congruent. As the vertical angles theorem states, the angles are congruent. Remember, a theorem is a statement that can be proved. We're going to go ahead and prove that. Now, you need to have some things in play, some postulates and other things. Postulates are things we have to assume to be true, or things by definitions, right? Definitions are created for a specific reason to help lead us to it. But hopefully some of these things will also take form as well. And I understand if this will be foreign to you when I do it. But we're going to write they say write a plan for a proof and a flow proof. We're going to work on two-column proofs for these. They believe you've already done two-column proofs and stuff. The thing is, you might have done it in IM1, or you might not have been able to based on the result of quarantine, the pandemic and stuff. So what I'm going to do, guys, I'm going to draw two columns here. I'm going to make a T table, and I'm going to do two columns. I'm going to have a statements column and a reasons column, and with every statement needs to have a reason. The initial statements I'm going to make are anything that is given and provided for us, and then we start building statements along the way, either from previous statements or by forming new statements that we think can assist us. Sorry, there was kind of the M's a little botched. The final statement will be this thing right here. Like, he is the murderer, right? That's the final thing. 1 is congruent to 3. These angles are congruent. That's the final statement we're going to make with validation from the things that led up to it. So here's where I'm going to start this thing off, guys. There is a given that angles 1 and 3 are vertical angles. Angle 1 and angle 3 are, I'm just going to put vertical. That's a given. Now, that doesn't mean anything to us right now. That's just by definition, vertical angles are angles that are opposite each other when two lines are formed. The important part is that two lines are formed. That's the important part that we need to talk about, because the vertical thing is just to help support the proof that all vertical angles are congruent. It doesn't help us. It doesn't help us prove it. It helps us make the statement. But it does help by knowing two lines are formed. If they're vertical angles, that means these are two lines. And if these are two lines, that means angles 1 and 2 are a linear pair because they are adjacent, because they form to make the straight angle, because they make that line. So angles 1 and 2, angle 1 and angle 2 are a linear pair. They're a linear pair because of, really, it's because of the definition of linear pairs. And the definition of linear pairs is two adjacent angles that form to make a straight angle right there. That's what they are. Now, what's the idea of definition of a linear pair? That they're supplementary. So that's important here. In fact, I'm going to, I'll just leave it right there for now. So my next statement I can make here, if they're a linear pair, honestly, I don't even know if I have to make this statement right here. I think I can leave it out completely if I just say that these two are supplementary. Measure of angle 1 plus measure of angle 2 equals 180 degrees. That is also because all linear pairs, sorry about the handwriting, are supplementary. I kind of want to go through this fast just as an idea. These two add to 180. Now, I'm going to echo these two things for angles 3 and 2. Angle 3 and angle 2 are also a linear pair right here. Angles 3 and 2 are a linear pair for the very same reasons as noted above. So I'll say angle 3 and angle 2 are linear pair. I'm probably going to run out of room for this one, guys. So definition of linear pair here. That also then means that the measure of angle 3 plus the measure of angle 2 equals 180. Now, why am I leading into all this stuff here? Because what happens is there are two different sets of angles that add to 180, which both share one of the same angles here. 1 plus 2 is 180, not literally 1 plus 2, 1 plus 2 is 3, but angle 1 plus angle 2 adds to 180, and then measures of angle 3 and 2 add to 180. Well, both these share a 2. Now, there's more math that I would end up doing in the process. I hope that you're okay with me kind of skirting on the side for some of this, guys. We're going to use these things called properties of equality, like the subtraction property of inequality, stuff like that. If I subtracted the measure of angle 1 from both sides, guys, I'd get that the measure of angle 2... No, hang on. I'll say this the other way. If I subtract the measure of angle 2 from both sides, I'll get that the measure of angle 1 equals 180 minus the measure of angle 2. If I subtract the measure of angle 2 from both sides on this one, I'll get the same thing. Measure of angle 3 equals 180 minus the measure of angle 2. I have two different things that equal 180 minus the measure of angle 2. That must mean these two things equal each other. So by the subtraction property of inequality, because I subtracted the measure of angle 2 from both sides here, and I did it down below, I make these statements. Because of that, the measure of angle 1 equals the measure of angle 3. Okay? They equal each other by, they call it transitivity as well as by substitution. I'll just say by substitution. We substituted measure of angle 1 or measure of angle 3 in place of 180 minus measure of angle 2 because they're equal to each other. So by substitution, that happens. Let me move this one down because I'm going to use that later. So one final statement I get to make, guys, if their measures are equal, Equal measures mean congruent angles. If these measures are equal, then their angles are congruent. Angle 1 is congruent to angle 3 because equal measures means congruent angles. Congruent angles. Whoopsie. And vice versa. Also one of those converse things. They're biconditional. Congruent angles means equal measures means congruent angles. And that is a proof. I didn't have to use a single number. Well, I used 180. But the concept is when they're supplementary, they add to 180. I didn't use number examples to make it work. I made something indisputable just from the nature of even as variables. You could put in any number for them and it will apply regardless. I can't say they're just equal because, but based on linear pairs adding to 180, I shared an angle there and kind of made it happen. So building a proof is going to take a little bit longer here. I'm not teaching you how to build the proof right now. I'm giving you concepts and what proofs look like, specifically the two-column proofs that we're going to be diving into a lot more. Let me do one more and then that'll be it for this thing. Let's do the alternate interior angles theorem. The alternate interior angles theorem states that alternate interior angles are congruent when lines are parallel. So say angle 3 is congruent to angle 5. That's the one they want to prove. Or they're saying measure of angle 3 equals measure of angle 5, which I'm actually kind of surprised with that they don't just say angle 3 is congruent to angle 5 there. I think they're actually stopping one step short of what they'd actually want you to do. I think you know what, I think because this is the book here, I'm just going to leave that out and I'm going to go to this one straight up right here. I know why they're doing that, but I think they're stopping one step short of actually making this final statement. We want to say alternate interior angles are congruent when lines are parallel. And guess what? We know the lines are parallel. You know why? It's given. It is given to us that line P is parallel to line Q, and that is very important. If that was not given, we could not make this proof happen. Now, in order to make this proof happen, there is one other thing that you're going to kind of have to know, and it's based on the postulate. There's a postulate on corresponding angles, and a postulate is a statement that we assume to be true. It's just by nature of it we do. And I know I've stated it in class, but I haven't probably stated it to the mass who may be watching this video, so I'll show that in a bit. But statements and reasons here, here's what I'm going to do, and then I'm going to plan it out, then I'll write it out. It's given that these two lines are parallel. When lines are parallel, two lines cut by transversal, corresponding angles are then congruent. And what I'm going to use, guys, I'm going to use two different sets of corresponding angles here. So I can say this one is congruent to this one, for example. I can say angle 3 is congruent to angle 7. That is a postulate. There's no way that these two angles can be congruent with lines parallel because they share a transversal here. And because this line is horizontal, guys, there's no way that I can't make this angle exactly match up with that angle just by a translation. It's a translation alone that states these have to be the same angle. There's no other way around that. That's why the corresponding angles one is a postulate. The other ones kind of go a little deeper. Once I state that those two are congruent, I will now tie in the two angles that I need. I need 3 and 5. So I'm going to relate 7 with 5 and say, hey, you know what? 7 and 5 are congruent. You know how I know that? You know how I know that? They're vertical angles. And we can now use that theorem. This is on a different tier of things. This is two parallel lines cut by a transversal, not just two intersecting lines. So I can use my vertical angles theorem to support that 7 and 5 are congruent. If 3 is congruent to 7 and if 5 is congruent to 7, then that will make 3 congruent to 5. That's a transitivity thing. There's this thing called transitivity that we're going to be using. It's an idea of substitution. It's a concept of substitution. So that's going to be our proof, guys. We're going to state it that way. There's more than one way you can write it, but that one really works well. But it all starts with the given, guys. Line P is parallel to line Q, and this is very much given. If that's not given, we can't use the corresponding angles thing we build after that. So you see, statement 2 is built as a result of this one right here. I'm going to say angle 3 is congruent to angle 7. This is known as the corresponding angles postulate. And because it's a postulate, we can assume it to be true. And this postulate is we can assume it to be true by its nature. I already mentioned that. So I'm going to mark it up too. That kind of helps. Mark it up. Angle 3 is congruent to angle 7. Angle 5, this is actually an easier proof than the last one, guys, as far as writing it out and everything else. Angle 7 is congruent to angle 5. Why did I choose 3 and 7 to begin with? Because I need to use 3 as a part of what I'm referencing. I also need to use 5. That's why I'm getting 7 and 5. Angle 5 is congruent to angle 7. Know how I know? That's the vertical angles theorem. That all vertical angles are congruent. And why is this a theorem? Because we had to prove that one to be true. And you know what? We did. We did. There's only one more statement I have to make, guys. I'm just doing 3 is congruent to 5 there. Therefore, angle 3 is congruent to 5. Whoops. The official verbiage of this, it's called the transitive property of congruence. These are things that I'd have to dive more into class with, but the idea is there's a reason behind it. And here's the thing. Whoopsie. Sorry, guys. The handwriting is totally bad right now. So here's the thing. My first statement led to my second statement, right? By nature of the lines being parallel, and this wouldn't work without it. By nature of the lines being parallel, guys, that made angle 3 congruent to angle 7. The corresponding angles postulate states that when two parallel lines are cut by a transversal, then corresponding angles are congruent. That's what makes that work. This one, I created this one on my own. This was a fabrication of not having to do with any of these two. I mean, I was going to connect the two, right? I was going to make a connection. That'll get to statement 4. But I made this up all on my own. This didn't have to do with lines being parallel. Vertical angles are congruent regardless of parallel lines, right? So that's kind of created on my own. And then I used statement 2 and statement 3 to make statement 4. If 3 equals 7 and if 7 equals 5, then 3 equals 5. That's what transitivity looks like. Transitivity says if A equals B and B equals C, then A equals C. It's that kind of thing. It's a form of substitution, if you will. 3 kind of took 7's place. If 3 equals 7, 3 takes 7's place. And it's of congruence because we're talking about congruent bits. Anyway, that's another nature of two-column proofs. I hope that kind of made sense. You're just getting the idea of it. You might not learn it all, but you were exposed to the concept. And the idea of proofs is these are irrefutable. You can't dispute anything that was stated here, and it leads to a statement for all alternate interior angles. What's an exception to this if I'm talking about alternate interior angles? There is not one, and that's why they're congruent. That's how the theorem works. And that is how proofs work regarding this stuff, guys. And like I said, the two-column proof thing has statements and reasons. You need to back it up. You can't just make things up. They're all created based on other concepts of math and things that you led from other statements, and that's how it works. So as we work more on that in class here, I hope that that little bit of exposure can get you somewhere. There's a lot of proof planning that we have to do, and there are a lot of statements and reasons we're going to have to make sense of, but that is the end goal. Thank you for watching, guys. I hope that this made some sense. Take care.